Good morning. My name is Terry Mandan. I am an IoT Global Black Belt from Microsoft. Today I will be presenting Effective Management of Equipment Resources with Machine Learning. With Sean Crabtree and Roland Scriban from Hitachi Solutions. Feel free to add questions to the chat window. We will be having a question and answer at the end of the session. By 2018, 6 billion connected things will be requesting support. The dramatic rise of smart machines and autonomous devices is driving radical shifts in business practices and individual behaviors. Global digitization and IoT are changing manufacturing. 25 billion connected things are forecasted to ship by 2020. 250 million connected vehicles are forecasted to have some form of wireless network connection by 2020. 49% of total respondents rate security concerns as a high priority with IoT inhibitor to the success of the IoT. 49% of total respondents think IoT's primary impact is for customer-facing products and services. 42% of respondents think that the long-term impact of the IoT creates significant new revenue or cost savings opportunities. Advanced technological capabilities require manufacturers to transform their business processes to enable systems of intelligence that help draw better insight out of data and convert it into intelligent action. Previously, businesses designed, built, produced, and shipped a product, then customers bought it, and that was the end of the cycle. Now organizations are building in continuous feedback loop sensors in product, aftermarket services, and customer feedback from a variety of channels. Transformation requires these rich systems of intelligence, which represent the combination of technology, people, and process that enable these feedback loops. These systems define an organization's competitiveness and ability to change the entire landscape of the industries which it participates. Manufacturers need to enrich their market offerings to deliver not just manufactured product, but also value-added business services to provide a complete connected customer experience. Connecting people, processes, things, and data securely across a company is the cornerstone of digital business. Digital transformation can be viewed in 4 main pillars that define how you take advantage of a connected experience to engage your customers, how you use productivity tools to empower your employees, how you streamline and use data to predict problems before they happen so your operations are stronger than ever, and how you utilize technology to create new revenue streams and fundamentally transform the products you take to market. We'll look into each of these in more detail. First, let me give you a key example of total digital transformation for manufacturers. We have a large utility customer in Canada that is moving away from traditional data collection by bypassing the traditional on-site historian and pushing their process data directly into the Azure cloud. Once in the cloud, they can take advantage of Cortana's rich set of services, including machine learning. Digital transformation is fundamentally changing business models. Every industry sees different areas where technology will bring dramatic change in the business models. Together with our partners, we want to share our solutions and examples on how you can be the disruptor in your industry. These pillars are why we are doing this webinar. Today, we are focused on equipment resources with machine learning, so predictive maintenance is key. Most companies who venture into machine learning start with predictive maintenance as the dollars are very large. Most companies with assets in the field or in a plant are looking at IoT initiatives. Engineering companies are quickly providing IoT services to their customers. Utilities are quickly adding large numbers of sensors to their operations. and manufacturing companies are quickly automating the plant floor. At this point, I'll hand it over to the stage over to our partners, Hitachi Solutions.
And thank you very much, and welcome to the Microsoft Hitachi Solutions IoT Machine Learning webinar. Today we will introduce you to the Hitachi Solutions IoT Predictive Service Hub with a special focus on machine learning. Briefly, a bit about Hitachi. We're part of the global Hitachi Solution Business Solutions Group. We're comprised of three main delivery arms: the Microsoft AX delivery arm, the Microsoft Dynamics CRM delivery arm, and our group, the Business Analytics and Collaboration Group. We deliver innovative solutions with more than 2,000 Microsoft-focused experts around the world. Today's webinar will be delivered by two Hitachi senior solution consultants. Let me pass this over to Rowan.
Hi, thank you very much, guys, for welcoming us to come and speak to you. Just a quick introduction about myself. I'm an architect at Hitachi Solutions. I've been with the company about 3.5 years now. I possess a Master's of Science from the University of Calgary, and that was primarily rooted in research methodology design and then also the evaluation and presentation of the results. I moved over into business data because I found that the challenges, the differences between the challenges that we demand of data inside of academia versus business were uniquely different. You deal with much larger data sets, often unclean data sets with a lot of siloed data as well inside of organizations, and it presents a really unique opportunity to look at data from a different way, try to resolve those challenges. I also co-developed the Business Intelligence and Analytics Certificate at the University of Calgary, currently an ongoing instructor there for about the past 2 years. And I not only deliver online, but I also deliver in-class sessions there as well. And I also help co-develop and I continue to deliver workshops that we deliver in conjunction with Microsoft around the Power BI service as well as the Azure Machine Learning services as well.
And good afternoon, I'm Sean Crabtree. I'm a Senior Solution Architect here at Hitachi Solutions. I have over 30 years experience in a variety of roles within the technology sphere as an evangelist, an implementer, as a Chief Technology Officer of a large consulting organization here in Canada. My career has been focused on a variety of areas including industrial IoT, advanced analytics and collaboration platforms. I do speak at a number of conferences around the notion of digital transformation and the digital workplace, and specifically how big data and IoT can factor into that. So let's get started. At a high level, here is our agenda. We're going to look very briefly at what are the major steps involved with analytics. We're then going to take a quick look at what a IoT reference architecture should look like. At that point, we'll introduce you to the Hitachi IoT Predictive Service Hub. We'll then have a demo of IoT supporting dashboards. We will follow that with a presentation and a demo of Azure Machine Learning. And hopefully, if we have time at the end, we will have an opportunity for a question and answer period, but we will be capturing all of the questions as we move along. So let's get started. Major components of an analytics solution. Starting from your left, data can be captured in many different ways. It can be captured from a business application, off-the-shelf application, and of course our topic for today is all around the Internet of Things, so a variety of sensors and devices. Data can then be ingested, and again, we can ingest data in many different ways. It can be bulk, it can be event, many different ways for that data to get there. At that point, data is processed, And we can look at a variety of methods for processing, whether that be the traditional ETL process, whether that might be event processing. There's many different ways we can do that. But once we have processed that data, we then have what hopefully is clean data, and we can start to report and visualize against that data, and we can take action and discover against that data. Let's take a look at a traditional reference architecture for IoT, and I think it's a little bit funny that we call it a traditional and that there's been so much written about IoT, but frankly we've been doing telemetry-based applications for many, many years, and IoT seems to become the marketing term for that, and that's fine. If it brings attention to it, so be it. Again, starting from your left, we have equipment of all sorts. Devices can be instrumented. We can look at industrial networks such as SCADA. But at the end of the day, there is just many different ways to generate and move that data. That data is transported in a traditional fashion that might be on premise. It could be in the cloud, depending on when these systems were implemented. But eventually, that data is analyzed and actioned by either a human or an application. Data may be stored temporarily, and then it's monitored, visualized, or reported on. So that would be a traditional reference architecture. Now we'll take a look at a more modern architecture and what that might look like. In that case, we now have the advent of intelligent devices along with what we refer to as traditional IoT devices, including low-power devices, but with the difference now of the opportunity for things like an edge-based network architecture or a Bayesian-type solution. So we have a lot more intelligence much closer to what is being monitored. Now we have data being transported, and frankly, due to low cost of communications, the high volumes of data that's generated, cloud-based solutions like Azure are very much the direction to go in terms of building out these functional solutions. Once that data is brought in, is collected, and it can now be actioned, and now we introduce the notion of a combination of cold storage for historical purposes and hot storage, which is our temporary storage. So this is where we start to see some of the differences between that traditional architecture and the modern architecture. And then lastly, now we can start to introduce the notion of artificial intelligence and machine learning that allows us to learn from what has happened historically, and maybe that allows us to start to consider visiting our models and looking at a break-fix model to a more proactive maintenance model or even a predictive model. And of course, that's what we're going to be talking about today. And then lastly, data can be consumed by a wide range of devices, including desktops, including mobiles, and many others. So with that, I will pass the presentation now over to Rowan, and he will continue.
Thank you, Sean. So what I'm going to talk about in the next section here is I'm going to introduce you guys to, at a high level, at a superficial level, the IoT Predictive Service Hub architecture that Hitachi has put together. And I'll introduce what technologies we've stitched together inside of the Microsoft Azure suite, and then also introduce you guys to what we consider processes that we need to develop or take into consideration to link the different components of the suite together here. So at a high level, this is the flow that we would see data move through the entire end-to-end model here. So we'd start with telemetric data, sensor data, pipeline data, streaming data, you name it, we pull it in. And then the next thing we do is we load that data into some sort of a storage. We pass it through our CRM Dynamics field services, run what we need to against machine learning, feed that data back into our storage sources and our CRM system, and then we would pull that out into our different consumption platforms, whether that be Power BI for dashboards and reports, or if you wanted something more interactive, you could use HoloLens or the bot framework as well. And we'll go into a little more depth in each of these as well and how we've used them together. But in end-to-end, we've consumed many of the services, and we've developed a model that stitches the Azure services together here to deliver the platform. So this is the end state for our Predictive Service Hub at high level. I will now break it down into components for us. So the first thing that we need to do is when a new device comes online or gets turned on, we need to register it. And we register that inside of our Dynamics field services. So we must develop some sort of an intake or an automated registration system because we don't want to be manually configuring every single device that we could possibly funnel through our data system or our platform here. So we need to capture some basic information about our devices. What's the ID of the device? What type of data is that device spitting back to us? Is the device part of a grouping of devices that would tell us information about normal behavior or normal ranges of the data that we intake? Is there certain locations that this device will be? And again, this will inform what the data that we expect to see coming out of that device would be. And then all of this helps us to begin formulating a template for the automatic registration of future devices or like devices, whether they come from different locations or similar locations, or if they're spitting out temperature data versus humidity data versus voltage data, or whatever that information might be. So we first must develop our configuration rules and the automated registration of new devices. The second thing that we set up and configure is the intake of data into our system. So as the data starts coming in, we must put that against some intake rules. So we got intake rules or event rules as the data starts kicking in through our hub and we stream it into our CRM system. We must place against this certain rules that tell us how do we classify this information, what the data type might be, what do we want to do with this information, whether we take that information and write it back to a database, or do we kick off a workflow within CRM, and that workflow might do certain things like write the data to an AX system or to a database system, or kick it through a predictive hub where we can run an immediate prediction algorithm against it. Or it might be something like kicking off an immediate trigger to reboot the device, shut the device down, or kick off a maintenance order as well. So when we pull that data in, we have process or groupings of rules that we run against the data coming in that tells us what do we do with that data next, write or action upon it. So once we decide that we need to write that data, what we do is we kick that data into a storage area inside of Azure. So we can use something like a Azure database, or we could use something like a data lake if we have larger volumes that we want to be capturing. And then once we store it in there, we can begin to structure and integrate our information together. And that allows us to take it to the next step, which is to feed it through our prediction algorithms or our predictive processes. So inside of our predictive processes, we can split it into two types. We can have a live prediction or a scheduled prediction process running against that. So with a scheduled prediction process, what we would expect to do is run it periodically. That could be nightly, monthly, whatever that is. And this would allow us to continue to tune and retrain models on a regular basis so that our models always stay up to date with the most relevant information that we have coming in. But it also allows us to run predictions on things that are not as urgent. So if we have longer term outlooks or longer term predictions that we're trying to make, things may not be as urgent. We can allow the models to run at a periodic basis. And this helps us to cap consumption a little bit. So depending on what the requirements for the devices are, requirements based off of the data event rules as it gets fed in, we can dictate whether something needs to be run immediately or whether something can be held off and run on a scheduled basis. And then that takes us to the live processes that we can run against this. So what we could do is feed this data in on a real-time basis if we need an immediate evaluation on a data point coming in, or if we just want to let the machine learning processes comb through our data on a regular basis or an ongoing basis to do pattern matching. And then finally, the outputs of that gets fed not only back into our data storage, but we also feed that data back into our CRM systems to augment the data that is already there. And then finally, the last step is the consumption and interaction with the data. So we can look at this out of our systems, out of CRM, out of a live stream of data, or even consuming live outputs of our machine learning. And we can do that through, again, as we said earlier, the Power BI interfaces, where we use the dashboards to disseminate enterprise-wide, or we also have special unique use cases where, say, HoloLens might be required, or a bot might be required to help us interact more immediately or with richer information. With that, I'll hand it back to Sean here, and Sean will go into a little more depth on each section of the integrated technologies.
Thanks very much, Ron. So the first portion of this solution is built upon the Azure IoT Hub service, and it provides us with quite a number of functions and capabilities in the end-to-end solution that we put together. The first part is it takes care of a lot of the issues as related to device connectivity. So as we can see here, we can support multiple types of devices, including custom devices through the software development kit. We support multiple protocols, and this is key for being able to work with a variety of data communication network solutions, whether they be high bandwidth, satellite, or low bandwidth. We can also, using IoT gateways, work with lower power devices, and of course we can still have our notion of an edge network or putting much more computational capability closer to the machinery. As that information then comes into the IoT Hub, we have a number of services that are run there. So we have the ability to operate with an event-based model where we can have a bidirectional communication with the device itself. We also have per device authentication and secure connectivity. And of course, this is important, and this is the big concern for many organizations looking to deploy an IoT solution. Within here as well, we have fairly complicated routing rules, so we can use a variety of network types, and depending on the availability of that network, we can make on-the-fly changes. And then lastly, we also support a notion of what's called twins, and this is the ability to have a physical and a logical device so that we can make changes to perhaps metadata or state information and understand what the implication of that is going to be. So as you can see, this is a solution that comes from Microsoft. It does require wiring up, of course. It does require customization, but it certainly gives us a platform for which to start. So that's our first major component. Our second major component is the Microsoft Dynamics 365 Connected Field Service. So this is a iteration, if you would, of Dynamics CRM specific for field service. It provides us with a number of functions. First off, it is the front end for managing the actual IoT devices. So deploying and provisioning devices is done through here, managing device state through here, and of course decommissioning devices. So it provides all of that front end for us, where in the past we would have had to create a custom solution. Equally important though, it also manages the life cycle of activity in a maintenance situation. So this would include things like incident management, scheduling and dispatching of both equipment and of course those valuable technical resources. It also gives us the opportunity to have inventory management, and in fairly large and complicated IoT-based solutions, just knowing what you have out there sometimes is a bit of a challenge. So this certainly provides that capability. It's very customer-centric, of course, so if you are working against service-level agreements with customers and you need to be able to keep them in contact with what's happening, it allows you to do that. And of course, it provides us with a lot of the logic flow. So there's an application development capability, workflow capabilities that allow you to customize the way your solution will work. As well, this platform provides us with a couple other things as well. It is the console or dashboard for human management of IoT devices. So if we see a situation where we are having an alert, a human can deal with that alert, or through the predictive portion of it, through a machine-to-machine connection, we can deal with that alert as well. In short, it's the action center for the entire solution, and it certainly provides us with a lot of functionality. I've spoken about the reporting interface. I'm going to hand this back to Rowan now so that we can take a look at how the dashboards are delivered for the solution.
Thanks, Sean. So what we wanted to take a little bit of time to show you guys was how we've configured the reporting part of the solution. A big part of why we would collect data at all is ultimately to be able to derive insight out of that data. That's a truism almost, or an obvious statement, but the science around how we actually present that information to provide a compelling and useful analysis is also a pretty important component of being successful in delivering these projects. So we would never just configure data and then just walk away, because what ends up happening in that situation is you leave the consumers of that information hanging. Unless you have someone who already understands that data very well, it can be a very big problem to overcome when you're trying to be successful or deliver something like this. So part of the Predictive Service Hub is packaging together, I guess, templates around what we can use for different types of incoming IoT data. And what we're going to show you today is a dashboard solution that we've developed around predicting maintenance or failure times on wind turbines for a wind turbine company or energy producing company. So I'm going to actually boot open Power BI, and I'll show you guys, I'll interact with a live dashboard, not a live dashboard, but a dashboard with real data hosted behind it. And when I say real data, that's in quotations, because this data has been cleansed and obfuscated to reflect mock data, so it's not client information. But nonetheless, we can see with a wind turbine, the first visual or the first view that someone would want to be able to see is at the farm level. I have wind turbine farms spread across North America, globally. Often these farms can be located in areas that are inaccessible, and if I'm managing all of the production off wind turbine sites, I'm going to have a very difficult time accessing all these sites at the same time. So I need to be able to visualize all of my sites together and use some sort of a leading indicator to tell us what sites are experiencing problems. So in this visual, you can see we have two key metrics that we're measuring against our wind turbines. We have the availability of our wind turbines, which is a reflection of how much uptime we have our turbines on any given site. And we want to maximize that uptime, because any time a turbine is down, that means it's not producing energy. And we also have energy efficacy, which is the ratio between what we could have produced and what we actually produced. So telling us what our conversion efficiencies are. If I select the month of July, you can see from my data here that there's one site in particular that is indicating we have some issues on it. And I'll just mouse over that site. So we have a wind turbine site called Slate, and it is located in Terrence Bay. Now you can see there's a availability percentage that is dipping just below 98%, so 97.6% approximately. Now that's pretty high, so you might ask, well, why do we care that it's dipped just a little bit, 2.5% roughly? So with any turbine site, because you're talking about potentially hundreds of turbines on a given site, at the site or the facility level, when your percentages start dipping, every single percentage point change is actually a large loss in terms of the production that you have. So immediately at this view, we can view all of our facilities, and we identify immediately which facilities need our attention. So let's take a look one layer down inside of the Slate facility. So our second slide here, or second dashboard here, is filtered to our Slate facility. And I will select the month of July as well, so we can see this information a little better. And I have mapped out on Slate Island here all of the different turbines and the locations based off of latitude and longitude. So each turbine has been pinpointed. Now what this allows is a site engineer or a site manager to be able to take a quick look every day at what's going on with their information, or what's going on with each of their turbines on site, as opposed to having to send out maintenance crews to each turbine and then to check it out physically. Off of some of the metrics that we calculate, they're able to quickly identify which turbines need targeted treatment or specialized treatment. In this case, we notice that a few turbines are showing that their availability percentages are coming down. And there's one turbine in particular here, if we mouse over, wind turbine number 27 at the southern edge of Slate Island is showing that it's dipped below 85% availability, meaning 15% of the time it is offline, and we want to understand why it's going offline. So let's take a look one layer deeper yet into the actual turbine 27. So on turbine 27 here, we now have a cross-sectional view of our turbine. And this cross-sectional view breaks the turbine down into rough components on the turbine. So you can see we have the blades of the turbine. Each of them send out sensor readings such as the vibration, the pitch, the yaw, the positioning of it. We also have information of the actual components inside of the production box atop the turbine. So we have a gearbox, we have bearings in there, we have crankshafts in there that will spin to generate the energy. We also have generators up there. So all of this feeds us sensor data. And we take that sensor data and we feed it through an ML program to predict how much time before each component fails. And then through that, we can come up with an evaluation of how much time before this turbine is going to start requiring some serious maintenance, meaning it's going to go into some definite maintenance cycles. It's going to be taken offline frequently or automatically triggered to shut down quite frequently. So in our case, we have at the very top there predicted days to failure, 107 days remaining. This is the output of a ML program that we'll show a little bit later that tells us this particular turbine has a predicted 107 days left before it will start to experience serious shutdowns or critical failures. We also track simultaneously information here around each of the components on the turbine and how many error events have been kicked off into our system. So as the turbine's spitting IoT data out, it kicks out event codes, and the event codes will tell us what's going on. So it'll read that temperatures are too high as an event code, for example. Or it'll read that if the turbine component was shut down for 10 minutes in order to cool off, or that it was overloading in terms of the electricity flowing through, or is vibrating too much, so it had to change the angle of the blade in order to receive less wind. So what we can do is we can select our gearbox here, and we can see that our gearbox is actually showing 287 events logged on it. And then the second component that we have a problem with is blade number 1, which is showing 83 events. So we see that the gearbox is where we're experiencing the most issues for the time being, and that our blade is also starting to show a significant number of issues. So what we've done here is we've gone from the farm level, where we can see all of our farms and all of our assets. We've drilled down to the site level, where we identify every single turbine, and we can go one layer deeper and look actually inside of each turbine, so we know exactly which component needs our attention. And all this information can be fed back through our Predictive Service Hub, where CRM would ticket the right maintenance activity and the right maintenance crews to come out and replace or investigate a given component. At this point, we'll jump back into the presentation, and we'll talk about some of the other ways that we consume this information.
Thanks, Ron. So we've looked at the Dynamic 365 Field Service solution that provides us much functionality. Embedded within that, we would have these Power BI dashboards that Rowan just shared with us, but there are other ways as well that that data can be consumed. And one of those ways would be through a mixed reality solution based on HoloLens. So basically what this allows a technician to do is to visualize a complex piece of equipment or machinery, be able to understand more about that piece of machinery without necessarily having to take it apart, but also have the ability to potentially overlay specifications or parts diagrams on top of that so that the technician can be most efficient at dealing with that. To give you an idea of what something like that might look like, we have a very, very short video clip.
This is based off of actual development work that we're doing. So you'll see this is an actual HoloLens video, and it's being filmed inside of a parkade. So you can see the background where the HoloLens projection was being rendered.
That's great, Ron. Thank you. Another way that a technician might be able to interact with the Predictive Service Hub is through the bot framework. And this would be a way for a technician to potentially interface with a knowledge base, to be able to ask questions, especially if their hands are busy and they're trying to do things and they want to be able to ask a question perhaps around what they should do next. But basically this is a method to be able to have that technician interface with the back-end system, to be able to ask those questions, to be able to move hopefully beyond a planned maintenance model, and maybe all of these pieces together allow us to move into a much more predictive service module. At that point now, we're going to take a look at the Azure Machine Learning capability. Ron's going to take us through a fairly detailed presentation around how this works, and I'll pass it back to you, Ron.
Thank you, Sean. So we talked about how we collect that data in, what we do with it when we funnel it into our Dynamics Field Service Hub, and then how we've visualized it through both dashboards and then also if you require a HoloLens or interaction through bots. Now, one of the most interesting parts of working with data and information is the ability to craft how we would model or predict certain events or certain information on our data, on our turbines. So in this case, what I'd like to do is pull out of the presentation and talk a bit to you guys about how we use the Azure Machine Learning Hub to run models against our data. Now, Sean promised a detailed presentation for this component. I must add that we will only go through at a superficial level. We'll take an actual hands-on look at some of the modeling exercises that we would go through, but this isn't the full gauntlet that we'll be presenting through. So let me take a quick tangent and talk to you guys about methodology first, because one of the great confusions that we discover with machine learning, with advanced analytics, is because it's very exciting and buzzy right now, a lot of people are rushing headlong to get into the actual crunching of the data. Everyone's keen to call themselves data scientists, but the true foundation of doing good analytics and prediction off of your data isn't about how much expertise, it is about how much expertise I have in the tools, but it's just as important to have a solid understanding about what's going on inside of my business today. So we make the argument that through good methodology, we actually want to and need to be doing good business intelligence, good traditional, descriptive, historical data analysis first to understand where those values can be drawn from taking certain data sets and pushing them through advanced modeling or advanced analytics type solutions. So let's ground ourselves. Let's use a methodology, the CRISP DM methodology, the cross-industry standard process for data mining methodology. This is a well-developed and established methodology that we find is not only useful for advanced analytics, but is also quite useful for just straight up traditional analytics. How do I action, or how do I solve or answer the questions that my business needs answered using the data that we collect? So with this methodology, the first and most important point is that we need to understand our business. Above anything else, having the good business acumen, the instincts to help us identify where we need to be looking for insights, being able to ask the right questions of our business, and then ultimately being able to make the right call based off of the data that we have is the foundation for any sort of data analysis, including advanced analytics. And to get good business understanding, we must first do traditional data well. We must first do descriptives and understand the historicals of our company well. So we understand, the first thing we do is we get a rich understanding of our business through good dashboarding, good business intelligence, good data integration techniques. Then what this allows us to identify is points or opportunities inside of our business where applying advanced analytics or machine learning strategically, like a scalpel, gets us the ability to predict some useful information we can consume to drive our decision-making forward. So when we have good business understanding, it helps us to craft the right questions we want to ask on our data. And crafting the right questions that we want to ask on our data helps us to collect the right data to answer those questions. So we craft the business question, and that business question in the example that we've shown today might be, I need to know how long before certain components inside of a given wind turbine is going to fail, and what that impact on the overall utilization of my wind turbine assets is. And that allows us to go back and say, well, what type of data and information do we need to collect in order to answer this question? When we go back and we start collecting that information, we now take that next step and we say, I not only need that information, I need that information in a good, trustworthy, and cleansed state. So I must then go through the exercise of preparing my data. When we're making any sort of a prediction, the prediction we make is a probability. It is never a 100% certainty. And what that means is that if we have garbage data or if we have errors inside of our data, ultimately that will lead to a lack of confidence inside of the results that we output. Everyone's heard of the idiom garbage in, garbage out, and this applies even more so when we're doing any sort of a predictive activity. So we collect the data, we cleanse the data. Next step that we do is we model the data. And this is really where the machine learning steps in and helps to fill the gap. With machine learning, what we're doing is we're leveraging the compute power of machines to run relatively complex or quite complex statistical models against our data. Stuff that would take us a long time to calculate out by hand or with a calculator. And we take the compute power of the machine and we put our data against it. We must structure our question and our data correctly against any given selected algorithm. We'll talk about that in a little bit. But ultimately, we use the machine to compute the outputs, the predictions. And then finally, we come back with the outputs, and we must again make a decision off of the outputs that we get, whether or not to trust that output or whether or not that output is giving us a high enough level of confidence in the results. So we don't just blindly consume the outputs of our model. We have to evaluate the outputs of our model and say, are we comfortable with this level of certainty or probability inside of our modeling? And then finally, deployment is an equally important step that often gets overlooked, and that is where we come back to the good construction of dashboards, weaving in the outputs of our analytics with traditional analytics, so the natural connection between our business problems and the solutions that we're trying to propose with our models is tied together tightly. At a high level, how does machine learning work? So this is that modeling step inside of the methodology that we went through. You have input variables that you take from your data sets. We call these predictor variables, or if you're doing an experimental methodology, it would be your independent variables. We take a collection of variables that we decide will help us to predict the outcome that we're looking to predict. So in the case of remaining days before a given component on a wind turbine fails, those inputs might be things like, what are the temperature readings on certain components? What are the vibration readings? What's the flow of voltage through certain components? What's the force that is being applied to certain components inside of our turbine? So we must identify through good business understanding, good understanding of how our business operates, what those input variables may be. And this part is a bit of an art as much as it is a science. So your instinct will guide you towards the early identification of some of those variables. And then we run it through the statistical model that we select. There are some rules to help us get started with this. And then we look to see what the outcome that we predict is in this case. And then finally, we consume it through a stream or by loading that data into a database, depending on if our needs are real time or if our needs are okay to be offset a little bit later. In today's example that we're going to walk through, we're going to talk about time to failure, or specifically days to failure of our wind turbine. And what we're going to do is we're going to pull, or I'm going to show you guys sample data from a single wind turbine at the turbine level, and we will run it through a simple regression model. We will use a couple different regression models, and the reason we use a regression model is we are trying to predict a linear output. So our outcome variable, or a dependent variable in this case, would be a linear output. So we use a regression model to create that output. We're also using something that we call a supervised methodology towards machine learning. So machine learning has a few methodologies. One of the most common and one of the most useful ones is supervised learning. And what we are specifically talking about when we say supervised learning is in our existing data set, we have the outcomes already captured for historical data, meaning we already have captured in our data how much time a given component or turbine has left to operate. And then we take that data and we're able to extrapolate it into the future. And that is how we're able to make the predictions into the future in this case. So with a supervised learning methodology, how we approach it is we take that historical data with our results already captured. We split that data into a training set and a test set. The training set is usually the larger set. You consume about 60 to 80% of your data, usually randomly selected from that historical set. And then you reserve a test set afterwards to compare your results against, to make sure that your model is giving you a high enough level of accuracy. So this is where the evaluation of our model comes in. So we split our training set off. We run it through the algorithm we decide based off of the variables that we have and the outputs that we're trying to predict. And then we evaluate the solution at the end. We evaluate the model against the test set, and we compare the actual results captured in that historical test set versus the predicted results our model runs off of that test set. And we decide if we're comfortable with the level of accuracy inside of that result. Now I'll jump out here and I'm going to show you guys Azure Machine Learning, the actual web portal here. So this is just to help get everyone a little bit familiar, a little bit more comfortable. We have a Azure Machine Learning portal here. It is a very, very streamlined and nice to use interface. I quite like working with the Azure Machine Learning interface. It is facilitated off of drag and drop functionality, so you can see each of the sections inside of my experiment here has been dragged and dropped from the menu on the left. I simply grab an element and pull it out. And so it creates a nice way to interact with my data that doesn't require me to write complex codes, making it easy for someone to get started. The only part that you need to understand is how to apply the right type of algorithms or models to your data in order to get the right type of result outputs or maximize the predictive power. So I'll walk through at a quick high level what we have here. We have the ingestion of our wind turbine data, and then we select off of our wind turbine data a subset of data, and we'll view that in a little bit. We split our data 80-20, and we take 80% of that data to run our models against, and then 20% we hold in reserve to evaluate the effectiveness of our models as an output. And as an example, let's pull in a couple of regression models that we want to give a spin on. So we talked about our problem being a prediction of a linear output. Let's pull in a boosted decision tree regression model, and then let's pull in a regular linear regression model just to make that contrast. So we have something a little more sophisticated and something a little more simple. And I connected my data up, split the data, and I have train and score and evaluate ready to go. I simply hit run. It'll be about 10 or 15 seconds to run through and process my model, and then we can take a quick look at some of the logic behind here. So what I've done, make sure that's run properly. What I've done on the second step, I did want to highlight this after it goes through correctly, finishes off. What I've done on the second step is we've actually taken that entire data set of features that we have. I'm going to visualize it here. And based off of a correlation, I've decided to select only a subset of features to predict. So you can see I have different types of readings, blade vibration readings, main shaft vibration readings, fatigue, hydraulics, temperatures, you name it, it's in here. And what I've done is I've correlated against our outcome variable, and I've decided to create a cutoff of a correlation score of 0.6 or higher. Rule of thumb dictates 0.5 or higher represents a strong correlation, but we can go even more rigid with that, or we can be even more selective with that and say 0.6 and higher. So that gives us about 10 input or predictor variables that we then select, 10 variables. We run our two different models, and then let's do a quick comparison of our two models. So if we look at the evaluation against that reserve set of data, we can take a look at some of the outputs of our two models here. Some of the important ones are root mean squared error or mean absolute error. That will tell us what the error terms on our model are. You can see we have lower error or variation about the prediction inside of our boosted decision tree. And we also have, this is an important one at the bottom, the R-squared values there that also are higher inside of our boosted decision tree, which means that we account for more variance inside of our outputs. So the decision that we want to make is to go with a boosted decision tree algorithm because it has lower error and a higher variance explained. And if we go into our model here and we can visualize the output, we can map our our initial historical data against our output data, and we can see how that relationship maps together. So you can see on the x-axis we have our original data, the actual data, and on the y-axis we have the predicted data, and that maps quite nicely together. You can see there's a nice relationship between the two. However, do pay attention that as we get further and further out in terms of time left, we lose predictive certainty. We get more and more error about our prediction. So if we're staying within a certain time frame, within say 30 days or 20 days, we have superior predictive power or superior confidence that our prediction is giving us accurate or near accurate results. All right, so that brings us to the end of our demo here. And we did want to add a quick plug in just to say what Hitachi does and some of the ways that you can engage with us. We come in and we will help your company to understand what a roadmap might look like for you to come from what your current state is today, and then to get you to a point where you can begin to do IoT or predictive type data off of, or predictive type services off of your data. We also come in and we'll help you guys train up as well. If you're looking to bring or train up or develop in-house skill sets around either building dashboards, configuring data, or if you're looking to develop in-house skill sets around how do you use machine learning and apply it to your business problems. And then we would also be able to come in and help you guys with actually a longer-term engagement, like a 3 or 4 week engagement to help you develop a roadmap and also get you some specifics around what costing and what the actual development plan would look like for your company if you wanted to move or advance yourself in some of these areas, either analytics or IoT or predictive analysis as well. So with that, thank you very much. Please do reach out, and if we have any questions, be happy to take them at this time. So it sounds like we have 4 questions. 1 question, just 1 question. Okay, that's good. The 1 question I have here is, are there other ways to do machine learning in Azure? And the answer to that is yes. So you don't have to use the Azure Machine Learning that we walked through today. The Azure Machine Learning that we walked through today is a good way to get started or to prototype or to pilot out some of the projects or analysis that you might have in mind. It's a low-cost, quick to set up, quick to fail, or quick to succeed type of a methodology, but it does limit you to how much data you can feed through. So if you're looking to crunch larger data sets on a regular basis, you would want to be using Microsoft R Server. And what you would do in that case is you would pull it out inside from a data lake into a cluster, and you would run your R services or your R server off of that. And you'd be actually writing in R code in that situation, and you wouldn't be using the nice GUI, the interactive interface. So there does require a little bit more technical depth in that situation if you were to try and do it in another area. But absolutely, there's the recommendation that we have is if you're looking to use large data sets, if you're looking to leverage more complex or custom packages, you can use R Server. Of course, you can plug in R code into Azure ML as well. Let's say you have a data science team that is producing the models and allowing other people in your organization to consume those models. You can use it in Azure ML, but you can also run it right off of your data using R Server or Spark ML.
So we'd like to thank you very much for joining today's webinar. Certainly, if you'd like more information, please contact Karen Ashraf at the number and email address there. As well, we'd just like to remind you there should be a survey at the end of the session that we would very much appreciate you taking the quick minute or so to fill it out. It would help us to understand perhaps better what we can speak about, how we might be able to deliver the information if we need more time or whatever. So again, we thank you very much for your time today.